I see some people I haven't seen in a long time in this list.
All right, I think we can get started. I'd like to welcome you for this new lunch talk at the Center for Philosophy of Science Online this semester. Before introducing today's speaker, I wanted to remind you of the events this week. On Thursday, the Cognitive Ontology seminar organized by the Center will be meeting at 10 a.m. EST time, so Eastern Coast time in the USA. If you are in Europe, keep in mind that at this point there are only 5 hours. There's only a 5-hour difference between Europe and the USA because you've moved to winter time and we haven't. So it's going to be 3 in the afternoon for you for continental Europe and not 4 as usual. So 10 a.m. we will have 2 talks on Thursday morning, one by Brian Bruya and one by Julia Ass. And on Friday, we'll have another lunchtime talk given by Center postdoc Mike Schneider on stabs in the dark sector. On Tuesday next week, there is no lunchtime talk because it's November 3rd, and November 3rd is election day in the USA, and we wanted to give all of you, at least all of our American listeners, the possibility to go and vote that day if they so choose. And indeed, we invite you to go and vote if you're American on Tuesday next week. Today, before introducing the speaker, I want to remind you how to ask a question since we're using Zoom webinar. If you have a question, go down your screen and click on the Q&A button. You can input your name on the text box, and during the Q&A period, after 1 US time, I will move you from the status of attendee to the status of panelist, and then you can ask your question directly to Nick and have follow-ups if you want. Today, it's my pleasure to introduce Nick Fillion. Nick Fillion is a professor at Simon Fraser University. He works on a range of areas in philosophy of science with a focus on philosophy of applied mathematics and with an interest in issues such as models and approximations. And we will hear of some of these topics today. Nick has been it's the first time that he is a center fellow, but he's been at Pitt before when he was a graduate student. So it's been a real pleasure to welcome him back, even so we are disappointed that we were not able to see him in person this semester. I'm sure there will be further opportunity in the near future. Nick has published widely on a range of topics, and I wanted to mention your book, but it turns out that somehow your CV is not loading on my screen, so I'm unable to give the exact title of the book, but I'm sure you've got it handy. Exactly, that's the best way to advertise.
It's thicker than Wandering Significance.
Which is really remarkable. But it's published widely on a range of topics in philosophy of science, but also in important questions in mathematics or about mathematical tools that can be useful for philosophers. And indeed, that's a book that Nick just showed us a few minutes ago. Today, Nick is going to be talking about the cogency of arguments involving approximations. Nick, the floor is yours, and I'll mute myself now.
You see my screen properly? Yeah? Good. All right. So, well, thank you everybody for joining today. I'm very happy to give that talk. It's part of a project that I've been working on for a long time. In a way, it's not the most polished part of the project, but I thought that would be a great audience to present to in order to get good feedback. So it's on the cogency of arguments involving approximations. And to get started? Well, let's start with a brute fact. And I very much love that quote from Bertrand Russell. Although this may seem a paradox, all exact science is dominated by the idea of approximation. And the idea is quite simple. It's just that, as a matter of fact, our theories, our models, our hypotheses, and what have you are just not strictly true. This is hopefully not controversial and something that everybody is aware of when it comes to science. But there are a few questions in the vicinity of that brute fact that tend to suscitate a little bit more controversy. The first one is, sure, it's a brute fact that there's a lot of approximation in science, but what about the normative question? Ought it not to be the case that science is not dominated by approximation? Instead of just thinking about the fact that approximation is all over the place, should we not work towards eliminating those? Some people say, apparently, don't let it dominate you, which echoes what Russell says there, presumably. Now, no matter what we think about this first question, and that's really not a question I want to discuss today, there's a second question, because for the time being and for the foreseeable future, and perhaps forever, science will remain dominated by approximation, and the question is just then, well, what are the practical implications of that? What should we do about that? And I think most philosophers accept the brute fact that I've mentioned, but it's not so clear that there's any sort of agreement about what should be done about it. So that's what I want to talk about a little bit more today. Now, in order to set up the discussion, today what I'm going to try to do is to explain some ideas that relate to approximation in a very simple way, not too much technical details. So I'll try to relate it to things that as philosophers we've all thought about at some point. So in order to get started, well, if we want to think about arguments, we have to think about the component parts of arguments, which are propositions. And we have to think about the sort of semantic evaluations of those arguments that we make. And the one we learn in first year, when we start philosophy, is, well, truth value assignments. And that's an important one. So then we ask questions like, hey, is the proposition P true or false? Or does P follow from a certain premise set, sigma? And that's the kind of stuff we study in classical logic, as you all know. But of course, we also know that we cannot deal only with truth value assignment. We also need to think about other things like probabilities. And then we're going to be asking, hey, how probable is that proposition? Or how probable is it given some other set of propositions? And that's the kind of stuff that we learn to deal with in probability theory. A third kind of assignment of values to proposition that is very common is has to do with modalities. That's also very important. We ask things like, hey, is P possible or necessary? And then there's all sorts of variations on that, depending on what exactly we mean by possible and necessary. Is it in a logical sense, in a physical sense, or what have you? And we also ask questions like, hey, what would happen if P were true? Well, those are questions that have to do with counterfactuals. And again, we have good formal machinery to address questions like that, whether it be modal logic or structural equation models, which are becoming, of course, more popular by the day. But there's a fourth type of assignment that is very common in scientific practice. And those are things that have to do with approximate truth. So then we are going to talk of proposition as being accurate, perhaps more or less. We're going to talk about degrees of truth. We're going to talk about truth likeness and things like that. And we ask, hey, is P approximately true? Or how close to the truth is P? And things like that. And then the question that presents itself, if we keep drawing the analogy with the first three cases, well, what branch of philosophy deals with questions like that? So think about it. And I think that the very fact that the answer doesn't come to us as quickly as for the first three things I've pointed out already says, I think, quite a lot about the state of philosophy as a discipline. So I'd like to build on that as we go along. Now, when we deal with, of course, logic, probability, modal logic, and things like that, there are open controversies about all of them. That's not the question. But at least we have some sort of understanding of where the main points of contention are, you know, what the main camps are, where the battle lines are drawn, and you know, who are the main figures on each side of those controversies and things like that. Now, when it comes to debates about approximation, I think one of the difficult things to grapple with is that we don't have really any of that. For the most part, the issues are not particularly well specified, and we don't really know what are the main things that are at issue. So of course, here I'm making a little bit of a generalization about the profession, which is a bit dangerous because the audience today is probably among the people who will be the most attuned to such questions. But I think as a sort of general assessment, that's still fairly okay. All right, so what I would like to do today is to try to articulate some of those contentious questions and present some of the concepts associated with thinking about argumentations as they relate to the standard way we learn to speak about arguments. So for the question is, what makes an argument cogent? And we learned some ways of talking about that from the time we start in philosophy. And the best known spiel that we have to provide about cogency is the one that we learn in deductive logic. So we are trying to figure out whether a sentence is true as part of an inquiry. And then there's a sort of approach which consists in trying to find an argument with premise set sigma and conclusion p. And if we can determine that this argument is valid and determine that each of the premises are true, then that gives us very good grounds, as you know, the best grounds really, to claim that P is true. So that started with Aristotle and Euclid not far after, and for good reason that sort of remains the gold standard for talking about what makes an argument cogent. Now I here describe what I call an aspirational type because that spiel is meant to apply to arguments that have strictly true premises and conclusion. It's not meant to apply for other cases. And what I'm going to do is build on that and try to draw analogies and disanalogies with that particular case. Now, of course, in philosophy, we learned that the deductive logic spiel is just one of the spiels that we have to take into consideration. And of course, induction is a big issue or a big tool. And there's not just one kind of induction, there is many of them. So we're going to have to also think about multiple kinds of inductive spiels about what makes inductive arguments cogent. And again, we have arguments that are meant to go from true premises to true conclusion. It's just that the connection between the two is not going to be necessary, but rather a defeasible one, which I symbolize with a squiggly arrow here. Now, I don't want to get into the detail of all those spiels, but for those of you who know John Norton's survey paper on induction, you will have, you'll be familiar with them. And if you haven't read those papers, you should, because I'm going to delay, or not delay, send you back to those papers. Now, it's not so rare in philosophy because of the way people often characterize induction in logic books to think that all good arguments have to be of one of two kinds. Either they are deductively good or inductively good. And that's because, well, inductive arguments are often characterized as just those that are not deductively valid, which is not particularly helpful. Casey Gannon and Kevin Kelly have a very nice way of making us see what's so bizarre with that way of thinking. They say it's as if botanists were to classify all plants as roses and non-roses, which is technically not wrong, but it's not exactly helpful if you're trying to do botany. So, of course, the non-rose category should be broken down, and if we do so, then we'll realize that there are many other kinds of arguments as well. And each of them will come with its own spiel about what makes arguments of that type cogent. So, you know, with the sort of assignments of values to proposition that I've mentioned before, and the sort of connections between the premises and the conclusion that we can consider, we can generate all sorts of combinations, and presumably for each of those types of arguments, there's going to be some way of thinking about whether arguments of that type are cogent. And just to give an example, there's this interesting book by Valiant in 2014, which considers how we should think about arguments reaching conclusions that are not true, but rather probably approximately correct. And that's a fun thing that shows that we can just keep iterating those value assignments to proposition. And then the question is, what, if any, arguments of such a type are good, and why? So we want to develop a discourse to answer questions like that. So the project, part of the project that I'm starting to present today is just to shed light on the fact that so much work hasn't been done when it comes to thinking about the cogency of arguments. Very often we just take our logic courses, we take our critical thinking course, maybe our formal epistemology course, and we kind of get that feeling that it's all been done and that there are a few things to clean up here and there, but that for the most part, it's been done. But I think it's not much of an exaggeration to say that most of it remains to be done. And it's not necessarily a bad thing, at least in some case, because as I suggested, there's a sort of explosion or proliferation of the types of arguments we need to consider. And then it would become a very taxing task to try to articulate precisely meta spiels to characterize what's good about them in general. So it might be a much better, much more effective approach to just try to deal with them on a case-by-case basis and hope that we get our judgment about them right. So that's not unreasonable to want to do so. However, when there's a very common argument pattern, I think then it's worth trying to articulate the general principles that allow us to assess such arguments, because it will allow us to develop good reflexes that will guide how we assess the cogency of such arguments. And to try to make my point that such good reflexes are important, I want to suggest that, well, because for arguments involving approximation, we don't have a great awareness of what goes into those assessments, we tend to make systematic mistakes. So I want to start with the so-called mapping accounts or inferentialist views. I'm sure many, if not all of you, are familiar with pictures like that. It's fairly common in philosophy of science. I'm borrowing that one from a paper by Sakazadeh, Philosophy of Science 2020, who criticizes those approaches in an interesting way. I invite you to read the paper if you're interested. But the idea is that this sort of view of representation, I mean, is appealing because it is solidly grounded in the deductive spiel that we have about arguments. So if we have a representation M1, which is true, and M2 logically follows from M1, then M2 is going to be true as well. That makes some sense. And that makes a lot of sense, right? We ought to think like that when M1 is actually exactly true. Now, the problem, of course, is that, as the brute fact I mentioned earlier suggests, it's typically not the case. Typically, M1 is just going to be approximately true. That's the best we can hope for. And that's where the way people talk about the consequences that we're drawing becomes, well, flawed. But we're told not to worry. We're told, don't worry. If M1 is approximately true and M2 logically follows from M1, then M2 is going to be approximately true as well. So don't worry, it's all going to be okay. And I don't think that it is. An applied mathematician seeing that request not to worry would be terrified. And for many reasons. And I'm going to try just to suggest a few ways of seeing why that's a terrifying proposal. But just to make clear that we're all on the same page, the maneuver that I'm trying to criticize here is one that really consists in starting from an account that is designed to apply to arguments that have exactly true premises and true conclusion, and then try to wiggle our way out when we are cornered and forced to face the fact that the premises are not exactly true, but only approximately true. And, you know, I read a lot of papers in this area, and there are two very common approaches, and it's very sad, I think. One is to just do as if the propositions were true and repeat the same spiel, and I don't know, pray that you'll get lucky and that it will work. And if you allow me to be a bit facetious here, I'd like to call that the DN account, for do nothing about it. And a second reaction would be to say, well, it's not the same, so we're not going to repeat exactly the same spiels, but the two situations are essentially the same, and we're just going to make a few minor adjustments. And again, to be facetious, we could call that the missing the kairos account. I'm told that kairos means decisive point. And as I will try to argue here, the decisive point is that the two spiels that we should have in mind are not essentially the same and are significantly different. So at the risk of being overly pedestrian, but I just want to make sure we're all on board, it's essentially just a reflection on modus ponens, or rather a slight meta-theoretical variation. We all know that modus ponens here, it's beautiful, it's excellent, there's nothing better we can do in life. But then we have to face the fact that things are only approximately true, so we are forced to consider this slight variation. And then, is it beautiful? Is it excellent? Those are the questions that we want to answer. Now, from the standard logical point of view, if P is false, we normally cannot say whether Q is true or not, right? That's just how it works. But then approximately true premises are not technically true. So then the question is, well, why would replacing false by approximately true change anything about that? Maybe it works sometimes, but does it always work? Does it typically work? That's what we want to understand. Now, there are two claims that are mistakenly assumed, and I'm going to try to explain why they are mistaken so that we should think that the answer is about no, it's not typically going to work. So it's often thought that truth-preserving inferences also preserve approximate truth. That's the second version of the modus ponens that I was describing. But also it's often assumed that two propositions with the same truth conditions have the same approximate truth conditions. So that if they're true in exactly the same circumstances, they're going to also be approximately true in exactly the same circumstances. And this is not correct. An example that hopefully is not going to be too difficult. Suppose we start with a sort of rough conception of approximate truth, according to which it's within a certain threshold of being true. So not too far from the truth, and by not too far, we mean within a certain threshold. Then we see that those valid arguments may fail to preserve approximate truth. So here's a little example. We have a differential equation. Why did I pick that one? Just because it generates what I think is a nice picture. That's the only reason. As you see, we start at time 0 and the trajectories evolve, wiggling their way. And after a certain time, we see that multiple trajectories converge towards each other. So the idea is, well, there is a point on the y-axis, or the x-axis here, I guess, since, anyway, the vertical axis, where once you cross that point, then after a certain amount of time, the trajectories will really go in different directions. Okay, so if you're close to one of those critical points, then just going on the other side would lead you to be on trajectories that go in very different places, right? So you could have an initial value that's approximately true within a certain threshold, but the solution that it would generate would be completely different. Okay, so that's very standard. And in general, there's a branch of applied mathematics called bifurcation theory, which is precisely about finding those really delicate points that you shouldn't cross. So some of you might be familiar with differential equations. So those are for two-dimensional linear equations, very simple type of equation. And the beauty with those is that there's only 6 possible types of qualitative behavior, which is exemplified by those 6 graphs here. And the red lines are lines that are determined as a function of the matrix A, which contains 4 parameters. And if you cross one of those lines, you're going to get a different qualitative behavior. That's just the idea. Okay, so again, here we have this idea that knowing those bifurcation points is essential to know whether approximate truth is going to be preserved by a valid argument. And that directly relates to things that normally people talk about under as sensitivity, stability, and things like that. Now, this sort of situation gives rise, occasionally at least, in philosophy of science to a fairly reasonable sort of skepticism about matters of approximate truth. And that's an example from Larry Lauden's famous paper, Computation of Convergent Realism, where he says, these should be urgent items on the realist agenda, since until we have a coherent account of what approximate truth is, central realist theses are just so much mumbo jumbo. Now, I learned the word mumbo jumbo while reading that paper, and now it's one of my favorite. But I think it's a very reasonable charge or request at the very least, and that we should answer it. And then the question is, what would be a good strategy to compellingly articulate a sort of spiel about the cogency of arguments involving approximation? And ideally, we'd like to find one that is along the lines of the way we articulate our assessment for deductive and inductive arguments. So perhaps the trouble is that we don't have a set of broadly understandable archetypes of such arguments, similar to the ones that we learn when we first encounter deductive and inductive arguments. In his, I think the title is Little Survey of Induction, the 2005 paper, Norton introduces that notion of an archetype, and I think it has great pedagogical value. And the idea is just to have some simply graspable cases to get our thinking going about a given argument type. Wilson calls that in a different context, getting the go of it. And I really like that way of thinking about it. So I'm not going to discuss those archetypes that Norton proposes because my purpose is not to discuss inductive arguments here, but I just want to mention that the idea is to have something that people can understand, or most people can understand. So that's what I mean by easily graspable. It doesn't mean that it's easy to account for, of course, because those may be very different, very difficult situations. Now, of course, many archetypes of reasoning about approximation have been proposed over the years, even if people don't necessarily call them archetypes. One of the oldest one in philosophy is probably Ernst Nagel's characterization of theory reduction, where we would say that Newtonian mechanics is an approximation to relativistic mechanics, and that's perfectly fine. Right? That is a paradigmatic example of what we would call an approximation. Peter Smith, in a 1998 paper, presents dynamical theories as being a sort of archetype of good thinking about approximation. He says that for those cases, the issue seems simply resolved. And I think to a large extent, what he says in that paper is correct, though there are some points to, of course, nitpick on. Since a lot of you here are in Pittsburgh, you will be very familiar with that book by Bob Batterman, where he discusses at some length asymptotic reasoning, renormalization, and a number of other techniques that are very common in physical sciences, which are great refined versions of good thinking about approximation. And I'm sure many of you will also be familiar with that book, Wandering Significance by Mark Wilson, that presents a panoply of amazingly rich examples going from drums to guitars to all sorts of things. I think the Archie comics are not so much about approximations, but anyway, there's a lot of good stuff there. And if I can, you know, completely shamelessly plug my things, I've been trying to show some philosophical relevance of things done in numerical analysis to questions like that. Now, one of the difficulty with those proposals is that, well, some are a bit too limited to reveal key elements, and I'm thinking especially about Nagel. It's a very special kind of talk about approximation. Other examples that people discuss are very rich, much more interesting in that respect. But sometimes, at least for many people in philosophy, they are a bit too rich for comfort because it's very mathematically and physically involved. And as a result, it's hard to determine what's the conceptual issue and what is just a mathematical complication. So what I would like to be able to do is to, well, give you a sort of idea of an idea I had, which is to try to explain the main issues that are involved with reasoning about approximation with a very brutally simple example that hopefully will already allow us to articulate some of the interesting points. And in order to do so, well, I was thinking, why not try to do something along the lines of philosophy of arithmetic? Because in a way, we don't study philosophy of arithmetic in philosophy because it's representative of all of mathematics. Because, you know, everything considered, arithmetic is a rather, okay, I don't want to say poor, but impoverished theory if we compare it, say, to real complex analysis or functional analysis. But the importance of it is that it already allows us to grasp very important point about mathematical reasoning and to think about those philosophically. And it's a fairly simple theory. I mean, we all know how to do counting and basic arithmetic, so we have some ground to work with. Now, of course, in arithmetic or exact arithmetic, there are no issues involving approximation. But fortunately, we can think about what a book that has never been written would look like. So imagine there was a book called Die Grundlagen der Floating Point Arithmetic or something like that. Now, some of you might not know about floating point arithmetic. I will try to tell you a little bit about it here. But the idea is that it's a very, very simple mathematical theory. And it already allows us to engage some of the delicate conceptual issues that are associated with approximation. Now, here I write as we use it in modern science because science today is done with computers, and computers solve mathematical problems using floating point arithmetic. So that's really the workhorse of modern computational science. Okay. If we look at the history of floating point arithmetic, it's surprisingly fascinating because today, you know, we use Python, MATLAB, and fairly refined software environment. And a lot of the important, delicate issues that I have in mind have now been resolved to a fairly satisfactory level. But the history of floating point arithmetic is packed with really interesting controversies. So here's a quote from an influential textbook. So when we think about exact arithmetic, there is no controversy here. It can hardly arise in the context of the exact integer arithmetic, so long as there is general agreement on what integer the correct result should be. However, as soon as approximate arithmetic enters the picture, so does controversy, as if one person's negligible must be another's everything. And that's very common. So hopefully the idea is that already by looking at some of those controversies, we'll be able to grasp non-trivial differences between the spiel we should give about arguments involving approximation versus the other types of arguments. And the beauty is that it's mathematically very simple. So what's a floating point number? Well, you know about real numbers, presumably. You've heard about irrational numbers like square root of 2 and pi and things like that. If you were to represent those numbers within a number system, like the base 10 system that we're all familiar with, there would be an infinite decimal expansion. And for a computer, that means that we need an infinite amount of memory to store it, which is bad sign, right? So we don't want to do that. So what did scientists, computer scientists in the 50s and the 60s decide to do? They said, well, let's just take the model of scientific notation that we're very familiar with. So here I wrote the speed of light in scientific notation. And what we're going to do is we're going to take a finite number of bits, and we're going to approximate all the real numbers using those counterparts of finite precision scientific notation. So here, that's a standard format called the float 32 format, where we have 1 bit for the sign, and then we have, oh, actually my lines are incorrect. Those are the 8 bits that should correspond to the exponent. And then we have 23 bits for that part here, which is called the mantissa. Doesn't matter. But you see, it's a bit just like finite precision scientific notation. So there's nothing too mysterious about it. But one result of that, as you see from the first picture here, is that, well, floating points are a discrete set of numbers. There are gaps between numbers. It's not dense like the reals. And moreover, the larger the number gets, the bigger the gap between 2 consecutive numbers are. And we're going to see that that's important to keep that in mind. But interestingly, James Gosling, the creator of Java, said about 20 years ago, 95% of the folks out there are completely clueless about floating points. So if you're in that group, don't worry, you're not alone. And the 95% he was talking about are actually computer scientists. So even among computer scientists, a lot of people don't really understand floating point numbers, which is kind of sad, but anyway. Now, floating point arithmetic can lead to surprising things. Now, if you have a pocket calculator with you, or maybe an app on your phone, you could try to calculate those 6 sums. And just look at them a little bit. I just changed the order of the various terms in the sum, so it shouldn't make a difference. And that's something that you should be able to do in your head. It should be 137, right? And it should be the same answer for all 6 cases. But if you say use float 32 in C or Python or MATLAB or in your pocket calculator, you're going to get 6 different answers. You're going to get 0, 17, 120, 147, 137, and minus 10, hey, a -1. Then you might ask, well, why is that the case? I don't want to get into the details because I don't have time, but that's interesting to know that, hey, there's a controversy here already about how we should think about a very simple sum. Suppose you try to calculate a Lorentz factor in special relativity, and again, you do that in float 32, then you have numbers that are very large. And if you try to do that in float 32, you're going to get the blue curve, which is a step function, But of course, if you inspect gamma, it should be a continuous function, right? Much closer to the orange line, which is done in a format called double precision. So it might seem like, oh, if we just have more precision, we solve all the issues. But really, if we were to zoom in to the orange line a lot, we would see that we would have, again, the same issue, that it would be a step function. Why is it a step function? Well, notice that the y-axis is scaled in a very special way. That's because there are no numbers, no floating point numbers between those two levels. Right? So this is why it has to be a step function. So in a way, all floating point functions are discontinuous. Another thing that is funny, if you take a discrete map, some of you might have encountered that before. That's the logistic equation, but it's the discrete version of it. And we just keep iterating it to try to figure out whether it's going to reach some fixed point. And then the question is, well, what would happen in the long run? Well, there's only a finite number of floating point numbers, so it would have to come back to a point that it hit before after some time, right? And that leads to the weird result that in finite precision arithmetic, all discrete systems are periodic, which is, again, an interesting thing to notice. But okay. That's meant to just show that in some important sense, those computations that I've just shown you are not giving the right answer. And we might be thinking, okay, double precision seems to be solving some of those issues, and it gives you better answers than single precision. And then that naturally leads to the next thought, which is that maybe we can make the following association. So more precision will lead to more accuracy, which in turn is understood as less error, and that hopefully will give us better results, better answers to the question that we are contemplating. So that's a very natural association to draw. But then the question is, well, should we always be more satisfied with a more precise answer? And typically when we are dealing with floating point arithmetic, the answer is yes. What else might we want? And that's fine. However, I'd like to suggest that there's another paradigm to consider according to which the answer is going to be no. Okay? So what we want to first realize is that often those computations are just fine. And then how should we think about it? Well, that presses us to emphasize two very important different questions. The first, which is, I think, conceptually easy, is this answer closer to the truth than this other answer? And the idea is that, well, the closer to the truth, the better. Well, why not? But the second is the answer accurate enough, or does it have the right level of accuracy? And this is a little bit conceptually trickier because there's a certain context dependency associated with that question. And I think, fortunately, we can already start to see clearly how that context dependency functions within the confines of finite precision arithmetic. So for that, we need to look at another book that has never been written, which is Finite Precision, more broadly speaking, which also includes something we have all learned in our high school science class, which is significant figure arithmetic. Now, in case you have forgotten, and I wouldn't blame you, we can get the gist of it just by looking at a joke, those bazooka joke. Anyway, some of you might remember those from the 80s. None of them are very funny, but fortunately that one at least makes an interesting point. So Bazooka Joe is showing a friend a fossilized bone. The friend asks how old it is, and Bazooka Joe responds that it is 100,000,003 years old. How do you know that? Asks the friend. Bazooka Joe responds, the museum expert told me it was 100 million years old, and that was 3 years ago. All right, so the joke is not overly funny, I grant that, but it's based on the following idea, that the following answer 1.00, oh, I forgot times 10 to the 8, sorry. But that's not the right answer. In a way, it's too precise. The right answer should be 1 million, not 1,000,003. And when we think about that, it is a sort of mode of thinking about approximation, which is different from the one that we saw in floating point arithmetic. And what's different is that here, whether an answer is good has to be assessed with respect to a certain epistemic context that characterizes certain uncertainty. So the way we express the right answer shouldn't have more precision than is warranted by what we know about the system. So here, more precision doesn't convert into better result. And that's the way in which we see a contrast between those two paradigms. Now, again, when we're dealing with finite precision arithmetic, it's extremely important to be aware of the fact that equivalent propositions do not necessarily have the same approximate truth condition. It really depends on how those functions are represented. So here I have written an equation for f of x and an equation for g of x. Those of you who are good with doing multiplication by complex conjugate in your head will notice that those are identically equal, that is equal for all values of x, so that f and g, after all, are just the same function. All right, very good. Now, if we use a finite precision arithmetic, say a 4-digit significant figure arithmetic, and we take the argument x equals 500, known to 4 digits, then computing it with f, and again, each operation is done with using significant figure arithmetic. Then we get 10, and for g, we get 11.18. It's a big difference. If I'm not wrong, that is 11.8% difference. And if everything were exact, we would have the following answer approximately. So we see that in some sense, g is closer than f. But then the answer is, well, which one is better, right? Of course, G here is better. But good scientific programming is based on thinking about matters like that. You have to be very sensitive to the effect of using finite precision arithmetic, and you also have to be sensitive to the consequences of doing things in different ways. Okay, so there's already not a lot of time left. So, so what I want just to stress now is that we have two distinct standards of accuracy already. They're not like full-fledged, perfectly well-defined standards, but at least they show that they are perfectly reasonable and different ways of thinking about accuracy. And they're going to lead us to assess things, matters of approximation, differently. So when we're thinking about approximation, it's not just about saying, hey, we perfectly know what is epistemically better, and we just want more of it. It's not like that. The second standard in particular raises interesting, tricky question, because in this case, the inference's quality depends on what we know about the premises. So as opposed to what we are used to learning in deductive logic, here there cannot be a completely sharp distinction between matters that have to do with truth or approximate truth of the premises and inferential strength. The two are very closely intertwined. So that's a new issue that arises there as well. And that's just the tip of the iceberg. If you start looking at numerical methods that are developed to deal with differential equations, you're going to see that there are many more subtle distinctions between different concepts of approximation, and that those are importantly different. So recently I wrote a paper on finite element methods in philosophy, which was a little bit weird. There's not many papers in philosophy about that. But it was a discussion of something that Gilbert Strang identified in 1972 as a problem with the finite element methods, which are sort of the workhorse of modern applied mathematics and engineering. And he saw, hey, those methods work very well, but they shouldn't work very well because they commit what are known as variational crimes. That is to say, they just violate boundary conditions all over the place. And this is a very big problem. Now, in order to clarify what's happening there, again, we have to distinguish different concepts of accuracy that correspond to different expectations that we should have about what makes a computation good and should make us judge things different and articulate our spiels about approximation in slightly different ways. Okay, so since there is already quite a bit of time that's gone, I will go straight to the conclusions. So what are the take-home messages? Well, first is that I still have work to do in order to make all those things as clear as I would hope that they would be. But at least I hope that there are a few take-home messages apart from that. The first being that, well, there are many types of arguments that we often don't pay much attention to, but that are very important in science. And I think we should pay more attention to those. Then for arguments involving approximations, whether they start from true premises or approximately true premises, there's an interesting plurality of standards of accuracy. I hope that there's a bit more awareness of the principle, of the formal principles governing them, or at least perhaps of the lack thereof, because there's a sort of context sensitivity that we're not as familiar with, say, in deductive logic. So I've talked a little bit about some of the concepts that are associated with articulating a spiel about the cogency of such arguments, sensitivity, bifurcation, and things like that. There are more, but only so much time. And hopefully we see that there are some major, like big difference between that sort of way of analyzing arguments involving approximations and how we say we do it for deductive arguments. And among the major differences that we should never lose sight of is that what logical equivalence doesn't translate into approximate equivalence. Truth preservation doesn't entail approximate truth preservation. And it's not so easy to sharply distinguish matters of truth or accuracy from those of validity or inferential strength. Now, if some of you happen to be better versed in applied math, you might be thinking, but that's not how we talk about approximation. And I know, okay? I know it's a bit artificial, but I'm just hoping that by presenting it in that way, it makes drawing parallels with other things we already know in philosophy easier, and that it does have some value at the pedagogical and philosophical level. So hopefully that worked out, and thank you.
All right, Nick, thank you very much for this really wonderful talk. So let me remind you how we're going to be working. If you have a question, please just write your name in the Q&A box, and I will promote you to the status of panelists so that you can ask Nick your question directly. It takes a few seconds for that transition to happen. Siddharth, the floor is yours. Go ahead.
Thanks. Yeah, so my question is about, so you suggested these epistemic contexts relative to which we have to ask what is the best way to specify it. So the example of the dinosaur aging is interesting, right? So you have 100 million years. It doesn't make sense to say 100 million in 3 years in that context. Now, the worry I'm trying to raise is that all this is going to sort of be susceptible to a Sorites paradox, right? So basically, at some point, you start taking off 3 years, you're going to get to a point where it's actually going to matter, right? It's going to matter that it's 100 million or 90 million or 100 million and 50 million, right? And those can always be created by adding up 3-year increments. So if you say a 3-year increment doesn't matter to the aging of a dinosaur, then you have to sort of make sure that you can, you also don't consequently say, just by deductive logic, also not consequently say that 100 million year or a 50 million year increment doesn't matter. So I'm just curious as to whether there's a good discussion of how one deals with that kind of a problem anywhere in applied mathematics or in, I mean, in philosophy, of course, there's a huge literature on the Sorites paradox and vagueness and all of that. But within this kind of scientific context, I'm curious whether you have a thought of that, because it seems to me if we are trying to develop a logic of this kind of reasoning, this would be an important component of that.
Yeah, you're absolutely right. By the way, I see you seem to like paradox from the questions you asked in the other lunchtime talks. Okay, so that's a bit of a toy example, right? Nobody really uses that in foundational science because, to my knowledge, nobody has found a way of articulating significant figure arithmetic in a consistent way. I don't think that's a consistent theory of arithmetic, okay? And there are many discussions, surprisingly many discussions, especially in journal in chemistry, it turns out. Chemistry profs and teachers seem to be discussing how to best do significant figure arithmetic to a large extent. But I think it's just inconsistent. I don't have a formal proof, but that's hopeless. In fact, significant figure arithmetic has played a role in the history of floating point arithmetic, and part of the reason why those other systems were developed instead of implementing something like significant figure arithmetic for computer arithmetic is just that it cannot be done. So, so that's a little bit of a toy example to keep the discussion at the level of arithmetic. In my work, I discuss another approach to error analysis called backward error analysis, and it capitalized on the same idea, but that actually is consistent and able to handle questions like that.
All right, thanks, Siddharth. Naftali,
Thank you.
floor yours.
Great. Hi, Nick.
Hi.
Yeah, you're on.
Hi. Great. So thank you for your talk. I really enjoyed it. I'm trying to figure out how the two parts fit together, because I'm totally on board with the second part about needing to think a lot more about approximation and reasoning about approximations. But it's less clear to me that it's useful to think about developing a logic for it or thinking about inferences that preserve approximate truth. Now, it might be that you're just sort of giving a negative result, that if you don't have a logic, you're going to make bad inferences. But I see you might want to respond, but.
Yeah, I think I may have not been clear enough about what I wanted to do. So I didn't mean to suggest we should develop a logic, as a sort of calculus or anything like that for talking about approximate truth. When I was talking about a spiel, I chose that word precisely because it's a bit of a hand-wavy thing. But mostly it's about not so much make the assessment mechanical, but at least identifying what are the things we should keep in mind when we make those assessments. Mm-hmm. So I don't know if it affects the question.
So I guess at least throwing me off is when I think about, even as kind of a rough heuristic, and I think about what we're going to start thinking about, reasoning about approximate truth. So someone says, so it's approximately true that the speed of light is 3 times 10 to the 8th. And then you say, okay, well, is that, useful? Is it good? What can I infer from that? And then as you point out in the second part of the talk, it depends on context. It depends what inferences you're making. It depends on how precise the answer needs to be. And so there's a whole bunch of parameters in there that are being weighed, including, the precision and the context, but sort of that seems to me a bit orthogonal to the notion of, like just saying that it's true, that it's approximately true, that light has, the speed of, such and such, that, and what I can infer from that, it just doesn't seem to help me to think about the other types of considerations that come up in the second talk. So even as a very rough heuristic or spiel, I'm not sure how helpful it is.
Well, so, I mean, the first thing I was hoping that would become clear from the floating finite precision arithmetic discussion is that, well, if you think you could answer the question, is a certain proposition approximately true, in the same way that we ask what is its probability or is it true or things like that, you should just give up on that idea, okay? That's not gonna happen. And I hope that just looking at finite precision arithmetic is already enough to convince ourselves of that. Okay, so if you have convinced yourself of that, then you can come back to the earlier claim, which is, oh, here's how you can think about approximation in philosophy of science. Think of it essentially as if you were just dealing with deductive argument and tweak things a little bit, right? Like we see it so often in the inferentialist literature. And then you wait there and you're like, wait, but we just saw, looking at finite precision arithmetic, that it cannot possibly be working that way, right? Mm-hmm. So then the promises that are made to us when when we are cornered and facing the fact that the best we can do is approximation, well, it's presupposing a completely naive way of thinking about approximation. So that's how the two parts are supposed to relate to each other. And perhaps I could have found a better way of explaining it, but does it address your concern?
Yeah, thank you, that helps.
Okay. You're muted, Edouard.
Thank you very much for this beginner's mistake. We have time for more questions. Please write your name in the Q&A box. But meanwhile, I had a question for you about the plurality of standards for assessing inferences in that case. And of course, it's not only a situation that you find for approximations. You find the same plurality in other domains, including, for example, when you have to choose your estimator in statistics, mm-hmm. right? They have many properties. They can be convergent, they could be unbiased, they could be efficient, and so on and so forth. And those don't always converge. And what you do, I guess, in this case is you depends on the context, right? What you want, and somehow that helps you choose the estimator you might want, depending on the context. So context here seems to be important to sort out which of these standards should apply. Is that, are you thinking along the same, now, of course, context is a kind of a magic black box, right? Somehow you're never really told exactly how context is going to be used, but there's something right in pointing out to context for choosing the right standards for, the right standard, at least for choosing your estimator in statistics. Do you have the idea that something along the same lines would work for inferences involving approximations? And if so, is it just as vague as its context? Or do you have something more to say?
Right, it's a hard question.
It is a hard question. I totally agree. No more than I had something insightful to say about how we choose the standards whenever there are conflicting standards. And of course, I gave the example of statistics, but you might think what happens in life when you have to make any practical decisions in life, right? There's a short term, the long term, there's happiness, there's what morality requires, there's tons of different standards you might want to use. So do you have anything to say about that?
There's a funny quote by John von Neumann, which is, people who think mathematics is difficult obviously don't understand how hard life is. But okay, I mean, there is a little bit that we can say. So I don't think it works exactly in the same way in the two cases. At least, I mean, I'm not a specialist or anything like that in statistics. But at the very least, what I'm familiar with, often in statistics, they will justify the choice of an estimator rather than another one based on broadly decision theoretic consideration, where you try to assess risk or something like that. Now, in the context of, say, significant figure arithmetic, you really are not taking into consideration things like that. Typically, for that, and in the approach to numerical analysis that I favor, the backward error analysis thing, what we mean by context is just specifying a margin of uncertainty for each of the components of the models that you are using. And then the idea is, well, there are a few different approaches, one being, if you give any answer that is compatible with some form of the model that is within the margin of uncertainty, then you would consider the answer correct with respect to that particular context. Now, it could be incorrect with respect to a different context. So here the idea is that the quality of your inference has to be judged with respect to that particular characterization of what you don't know about the system. Now, it's hard to put sharp boundaries on what you know and what you don't know. Quantifying uncertainty perhaps would end up, if you try to do it rigorously at a statistical level, perhaps that would come back to the same considerations that you were thinking when talking about parameter estimation. I haven't thought about that yet. So anyway, on that say prima facie, there's a difference, but it might be that if we dig deeper, they come back. Yeah.
Cool. Thanks. So Colin was with us, but somehow has disappeared entirely. So John, you're next.
Nick, thank you very much. That was a wonderful talk and very stimulating. I'll tell you why. I often use approximation talk, and whenever I do, I feel uncomfortable because I know that something not right is going on. I don't quite know what it is. So I think to have you lay it out like this in such stark terms really, makes me think. So I feel like we're at a kind of an impasse. Where do we go from here? Here's a suggestion. I don't know if it'll help, but maybe it will. I think there are multiple senses of approximate truth being employed here. And part of the trick might be to start separating them out and then treating them differently. So let me give you two extremely different senses. And the question is, can we find a way to characterize them? So the first one can be characterized by a modifier portability, let's say. So here's an example.
Sorry, what did I missed it?
I'll say modifier portability.
Okay.
So here's an example. It is approximately true that pi is 3. Okay, now that we would normally take to be equivalent to saying pi is approximately 3.
Mm-hmm.
So you see, we've taken the word approximately and moved it to another place. I think we're pretty much capturing. So that's one type of approximation. But then if you look at the sort of examples that Loudon would be thinking about when we say Newtonian theory is approximately true, well, what do we mean there? Well, we mean if we assume that general relativity is a better theory or the true theory, take your pick, what we mean is in the case of very weak gravitational fields, general relativity can return us a structure that has the properties of a Newtonian potential. Right? Now, I don't see that modifier shift can help us there. But what this suggests is that we just need different ways of thinking about these two cases. They're quite extreme, and there are probably cases in between. What I want to find, if possible, is a kind of operational characterization of the different types. Right? That, you know, if we can say this approximation is characterized, this approximate claim is characterized by operator portability. That one is characterized by, well, I don't know what. Maybe we can go. Anyway, these are just thoughts, but thank you for just a really stimulating talk.
Well, I'm glad you liked it, because I mean the idea of presenting the discussion like that was influenced by some of the discussions in your seminar. So I'm glad you liked it. But also, yeah. So your first reaction, I think, is correct. We should be somewhat uncomfortable with talking about approximations, and we should be highly suspicious of promises that it doesn't introduce new complications. So that, I think that's right. As for the modifier portability that you mentioned, in fact, Peter Smith in the 1998 paper that I mentioned talks about that quite a bit, and I agree with you. That it's an important way of thinking about it. I'm not sure just how much work it's going to do. I still need to do more thinking about that. But it's been on the back of my mind for a while. I just don't have an answer that I'm willing to share at the moment. Finally, you know, about identifying different senses and characterizing operationally how they function, that is what I would like to be doing. And I know how to do some of that for some contexts that are a bit more technical. I was trying to at least get a feel for it at an elementary level. And there are also additional complications, because now I was dealing with essentially real valued approximation. And I'm sure you're familiar with measurement theory of Dana Scott and Patrick Suppies. If we take other sorts of concepts that work on different scales, then the notion of approximation becomes even more convoluted. And yet, it's not unreasonable to want to apply it to such quantitative concepts as well. So your suggestion is well taken. I'll just keep working on it.
All right, thanks, John. Colin, welcome back. The floor is yours.
I had the battery has started dying on this old laptop without warning me, so I lost my connection. Anyway, thanks. It was an interesting talk. I think I was similarly a bit puzzled, as Naftali was, about how much of a formal account you wanted, and maybe I was partly misled by, or into thinking this by something that I recall from the last slide, but also in your sort of pointing at in that original sort of three-part rectangular block diagram, you know, focusing on the inference, right, which makes it look like we want some story about the inference, when in fact some of the discussion seems to be more about the pragmatics of the propositions involved and when it's contextually appropriate to use them. But going back to the issue of the inference, I was also maybe surprised that you didn't talk at all about fuzzy logic and Zada's work here, which does attempt to give us a formal account of something like approximate reasoning, or has been deployed for that. So I'm just wondering why you draw the line there or didn't go there.
Good. Okay, so concerning the first thing you mentioned, when we talk about computation, we often don't think of it in inferential terms. I think it's a fairly natural approach. However, if you start to look at it in perhaps at a more technical level, then really computation, I think, ought to be regarded as a form of inference. Okay. Now, for a 15-minute presentation that I was intending not to be too technical, I decided not to force that upon people listening to the talk. So this might be why the parallel is not as clear as I would have hoped it to be. So my apologies, but I want to promise you that deep down that is the case. About fuzzy logic. I think fuzzy logic is not going to work. It is oversimplifying matters in a way similar to why I think Popper's account of truth likeness cannot really be adapted to do any of the work we have here. And part of it is because, well, so if we, suppose you take a differential equation and you just try to solve it. Right? Now, that differential equation is associated with a number of claims about what are the forces and the bodies in a given system. And basically, the differential equation is just the sum total using, say, Newton's second law. And when you deal with an approach like Popper's or the fuzzy logic approach, it takes all the premises and judges individually their closeness to truth. And it's going to tell you the conclusion is going to be at least as close to truth as the worst of the premise. And it just looks at them separately. But what's important here is to look at the combined dynamical effect of putting all those premises together, right? And I mean, perhaps there's a way of tweaking this fuzzy logical approach to deal with that. I don't see how to do that immediately, but my first reaction is definitely, if you want to get the talk about approximation correct, you really need to take into account the joint dynamical effect and not look at their truth likeness or degree of truth separately.
Yeah, good. So that actually prompts me to ask another question I had in mind here, which is, of course, most of your examples deal with something like numerical approximation. But I think that there's another notion floating around here in the broader context of approximate truth or truth likeness discussions, which is something closer to similarity than quantitative precision or lack of precision. And you know, there's this old quote from Goodman that similarity is a quack imposter going in places where it doesn't belong and all the rest of it, right? But I think that one thing that you point out in your response about the fuzzy logic, and I take that on board quite seriously, is that it's not going to work to collapse everything to sort of a single dimension. But similarity is really a multi-dimensional notion, right? So if you just come up with a single similarity score, that's going to fail as well. Everything is similar to something else with respect to some dimension or dimensions of that similarity. So I'm wondering to what extent thinking in terms of more of a multi-dimensional measure, and then thinking about the ways in which, for lots of scientific purposes, we want just something like the three most, we want to do some sort of factor analysis on those dimensions. Go, these three dimensions are the ones that really give us the most predictive power and good enough quantitative precision, and all the rest of it is actually a step in the direction that you'd be interested in going.
Okay, that's a great question. Again, those are things that are on the back of my mind. And there are, I mean, very many directions to go into. So I was, as I mentioned in answering John's question, I was mostly dealing with sort of real valued quantitative concepts, because I think those should be the easiest ones to deal with. And even with the easiest ones, it's a mess, right? Now, if we come to classificatory concepts, like those that are binary, right? Is this an atom, or is this a rock or a table? Or, typically when we talk about, when we have in mind concepts like that, we're more intuitively inclined to talk about similarity than approximation. I think that might be what you had in mind. And I mean, this is extremely hard. I mean, I think it's also a sort of natural attempt. Perhaps what you had in mind was something like garden force conceptual spaces when you talked about factor analysis. I don't know.
Yeah, I mean, that's one view or theory in that space. There's quite a bit of other work here, and also in sort of doing sort of language models and so on, semantic vector space models and that kind of thing. But yeah, I mean, going back to the bazooka one is a toy example, as you said, right? But there's a sense in which 100 million versus 100 million and 3. What's funny about the second one is, as you correctly pointed out, is it sort of indicates more precision than is really there. But in terms of sort of utility for, in terms of approximation, it's just as close, give or take, plus or minus 3, right, as any other number would be in that range, right? And they're quite similar numbers if you focus on the most significant digits rather than the least significant digits, right? So I'm not even sure that we can, well, I guess I want to push a little bit that I think even notions of similarity might apply in these numerical estimation cases as well.
Yeah. So I find the concept of similarity interesting, but even, I mean, I find myself getting increasingly comfortable talking about approximation, even if it's messy, and I'm still not comfortable with similarity. So it's not that I don't want to answer your question, but I find it very difficult. But you're right about the floating, about the Bazooka Joe example. I mean, in applied math, we often say sometimes one is a very great approximation to infinity, or very similar, because for numerical purposes, it often plays exactly the same role. It's a contextual thing, really. Yeah, I don't know what else to say.
Yeah, no, that's fair enough. And I think the notion of similarity is sort of another place where there's under-theorization by philosophers on this, right? So
yeah, I'm on leave now, so part of what I intend to do is to actually catch up with all those aspects of the literature and try to make sense of it. I'm sure a lot of good stuff has been written, but at the moment I'm not too familiar with it.
Right. Yeah, we should communicate a little bit, because some of the information theoretic measures of similarity I think are interesting for certain purposes. So I also really liked your point that, look, there are going to be many different inference patterns here, and there probably won't be one account that fits them all. And so understanding what is the right way to think about approximate truth in these different applications, I think, is a really good project. So, yeah.
Awesome. Thanks.
All right. Thank you very much. Marianne, the floor is yours.
Great. Thanks. Can you hear me?
Yeah.
Okay. Well, Nick, thank you for this talk. This was really interesting. I echo what others have said, that it seems like, I mean, I'm convinced that, yeah, there's like work to be done here, unexplored territory. And so the question I have is just kind of on a big picture scale of thinking about those areas in contemporary science, the working scientist who deals with models and comes away with a good day's work and says, well, what I got was approximately true, or I'm sort of satisfied with this, and getting, yeah. So I'm curious about, like, I mean, you said at the very beginning that you think this is sort of commonplace and uncontroversial, and I think that's fine. But I'm curious about, like, which specific examples are from actual scientific practice you think are the most important to get a handle on, and in particular, if you thought yet any about, and maybe this is just sort of naturally future work, but about cases where multiple models sort of come together and correct each other in significant ways, and that like that plurality of models is key to an actual scientific enterprise saying, I'm okay with this level of accuracy or something like this. And of course, if Sandy's here, maybe she can sort of pipe in with more details on this. But I'm just curious if you've thought about that at all, or ways in which applied mathematics might have something useful to say in those contexts. I mean, like Poisson approximations come to my mind as the natural place to look for sort of convergence from multiple angles.
Thanks for the question. I'm contractually obligated to say, of course, applied mathematics has something to say interesting about it. Okay. Some of the best paradigm in science would be, I think, parameter estimation in statistics and numerical analysis, which is about computer-based computing. I know it sounds redundant, but yeah, I think those would be some of the main cases. I've been in other places trying to argue that there's this branch of applied mathematics that's called perturbation theory, which is about trying to figure out what the consequences are of distorting various parts of a model. And I've tried to argue that this really should be our go-to paradigm for how to think about matters of approximation in general. So since pretty much all of my talks and papers say that, I thought I would try to say something different today for once. But yeah, so that would be the answer. So what's perturbation theory? Well, people learn it typically in quantum mechanics or sometimes in statistics when they prove the central limit theorem or things like that. Those are instances of perturbation theory. And people think, oh, perturbation theory is those instances of it, but really it's a much more general way to think about variations in 2D models more broadly. So that was the first part of the question. What was the other part? I'm sorry, I forget. I know I wanted to say something about it too.
Yeah, yeah, curious if you've thought much about cases where what's driving the scientific inference or a scientist's sort of comfort level with a certain level of approximation or known inaccuracies even is driven by like a multiplicity of models that can correct each other, and the cogency maybe comes from multiple models hanging together in a useful way.
Okay, good. Sorry, I forgot. I think, I mean, people like to talk a lot about inconsistent models these days for good reasons, I think. But I don't think people in science use inconsistent models, at least not in applied math, as much as people seem to think. And here's why. It might look like it, but when I was talking about values we assign to propositions, I wrote a little etc. And that's because there are other important things there that I didn't include today. And one, I think, is what we could call local truth. So truth at a certain scale or in a certain region of the phase space or things like that. And I think it's going to be very standard to use different models to represent phenomena at different scales and in different parts of the phase space. There are those examples of fluid flow in pipes where you're going to use a different model to calculate the flow near the pipe and in the middle of the pipe, or what is this, the Prandtl phenomenon for airlift. Or anyway, that's in Mark Wilson's book. There are tons of those examples. And that's also something that that perturbation theorists deal with quite a bit, and they call it matched asymptotics. And the idea is you develop different models for dealing with different parts of the system, maybe at different spatial or time scales or in different parts of the system. And then often they will try to find ways of making those match together. But sometimes they don't, and they just try to avoid talking or saying anything about the regions where the two would overlap. So I think they are very great cases, and then that leads you straight into the sort of stuff that, well, a number of people, but I'll mention Bob Batterman and Mark Wilson, since I've learned a lot of that from them. So, so those would be great examples, I think.
All right, we're already at 1:30, so I think we're going to be stopping here. Thanks, Marianne. Thanks again, Nick, for this wonderful talk, and I guess we can't clap. Self-congratulate. That was a really great talk and a really good Q&A. So thank you very much, and we hope to see most of you on Thursday for the Cognitive Ontology seminar, and on Friday for Mike Schneider's talk. So have a good day and be safe.
Thank you. Bye-bye.
Bye.